Hello everyone and welcome to this video about JSol'Ex 4.4, and I want to start with an introduction where basically I'm going to say that this version compared to previous releases has some really nice changes in terms of visualizations, and that's quite different from the previous releases where I focused mostly on improving stacking and whatnot. So let's get into it right now. And before we start with 4.4, just because I didn't do a video for 4.3, I'm just going to show you something. So here you have GPU support is enabled, and that's an experimental feature that I recommend that you try out. And you can go into the advanced parameters there and check this box, which is GPU acceleration. So this will not make the reconstruction faster because this is basically I/O bound. So the disk, reading the disk is basically what takes most time during reconstruction. However, for everything else, like the processing of images, stacking, in particular stacking, this can be much faster if you activate GPU acceleration, so try it out. But now we're going to go with the new features of JSol'Ex 4.4, and to show you that, I'm going to process a file that I captured this morning. And let's go into auto detect and let's process with my selection for now. Okay, so interesting. So it detected sodium, which is not the case, but that's going to be interesting because one of the changes in this version is that before, to figure out what JSol'Ex was detecting, you had to read the logs and figure out, oh, actually it found that it was sodium. And why did it find sodium? You go to the graphs and you have this view, and it doesn't quite look like sodium. So now this indicator is much more visible to you to actually check that you are processing what you expected to process. And this is true for the detected line, but also for the tilt and the XY ratio. So now let's go to the options and try to figure out why it actually wrongly detected these wavelengths. And if I go to the observation details, I can see that I actually selected the wrong instrument. I'm not using a SolEx here, I'm using an ACG 700. So let's go and go with, click the missing SAGs, and there's this MLastro here. So let's click on that. And now I have all my processing parameters okay. And given that the MLastro has different optics and the optics are different, so the dispersion is going to be different, so it explains why it detected the wrong line. So now I can do that and process again, and now the detection is correct, and it says H alpha, right? So much better for us, and it's important because we want this graph to be scaled correctly. So two things which are important. The first one is the SAG that you use. So you select in the observation details the correct SAG, and then the pixel size of your camera is also super important to get this graph correct. So now we have this image, and let's go with the new visualizations that you have. So maybe you noticed that already, but there's a new 3D button there. So I'm going to click on that, and now you see what it is about. So it's basically projecting the 2D image that you got from a flat sun, and actually the sun is not flat, and it's a ball and a ball of plasma, and this basically projects this image onto a sphere. So you can choose to show the prominences or not, and you can also, so it has this slight animation when you start, but if I click on something, I can basically rotate, zoom in, and then you can export the image as you see it if you click on export PNG. But I'm not going to show that. I'm going to show you what happens if I click on export video, and then you can click on save, and then you can choose the resolution. And I'm going to stay with the lowest resolution for now because it's going to be faster for this demonstration. But now I'm going to click annotate images, which is going to add some annotations there, which are basically the observation details, like who was the observer, what was the instrument being used, etc., etc. So now I'm going to do that, and if I go into the file, so I can right-click on this image and go into this output directory, I have a GIF animation, and I also have this MP4 file that you can use to share on social media, whatever you want. So the resolution is low here. It's 500 by 500, so it explains why you have this aliasing. But if you go with a higher resolution, basically it's only going to take more time to process and export the video, but it's going to be higher. So your choice. So this button is available on all the different images. So if I go to the mixed image, typically I can do exactly the same. And then you have this beautiful colored image that you can share. And I'm sure that some people are going to like that. The prominences thing is a bit weird because obviously when you have prominences, we don't know where spatially they are. So the only thing that we can do is basically project them as a ring around the sphere, but that's pretty much all we can do. So you may want to have them or not. Again, that's your choice. Something I must mention is that if you are using Mac OS, MacBook, MacBook Pro, whatever, this feature is not available, or maybe it's going to work by luck on your machine. But for all the trials that I've done, basically it was not working. My problem is basically that I don't have a Mac, so I cannot really test that. Maybe there's a solution, but I couldn't figure that out. And yeah, so unfortunately, if you have a Mac, this feature will probably not show you this button, meaning that the feature is disabled for your computer. Anyway, so let's move on and talk about the other improvements that we have here on the graphs. So you see 3 new buttons, and we're going to talk about all of them. First of all, let me remind you what this is. Basically, this is the profile. So if we look at the reconstruction, so when we click on the graph, basically what you have is the profile, and there are different views. I'm going to zoom there. So I clicked on something, and you have different lines like the frame intensity, the line intensity, continuum. So you can actually click on these buttons to disable some of them. And frame intensity is actually the one corresponding to the these dimensions. So we have variations of intensity of pixels, and if you take just a slice, like a vertical line there, that's 2D view that you have there. So you have the average value, which is the line intensity, and you have this frame intensity. Yeah, this one is actually for base 2K, and this one is the one that we measured. And that's good, and that's done on the average image. So we take all the frames, we take an average of all the different frames, and then we compute this graph. So that's a 2D view, but what would be interesting is to actually have a 3D view of that. So we can click on that, and that's exactly what we have. So here, instead of having just the average image, what we have is on one dimension the wavelength that we are observing, and the other one is a spatial dimension, which is the slit dimension. So we are basically observing the spectrum depending on its position on the slit. And it's interesting because this view can help you diagnose some issues with your slit, typically. So sometimes you're going to see like a line from above which is standing out, and it is often the case that it corresponds to dust on the slit, or it could be a defect on the slit, like the slit is not evenly wide, and sometimes this graph can help you figure that out. Also, you could potentially see some issues with vignetting, that you would see that the intensity falls down on the edges. So yeah, this graph is basically something which is interesting to see the defects on the slits depending on the position on the slit, versus this graph which is basically averaging all the positions into one. So the second thing that I want to show you is this spectral cube, and it shows you a pop-up with some information, because this is going to be expensive. So the default parameters should be okay for most people. You can try to increase them if you want more resolution, but the higher resolution you go, the more data you're going to generate. Like if I go to this, it doubles basically the amount of required memory. Actually not, because there's the baseline, but yeah, you see the idea. So you can choose the resolution, and then when you click on that, let's see what it's going to produce. Okay, so now we have this graph in 3D, and let's try to understand what this is. So we have 3 dimensions now. We have the slit dimension and we have the frame dimension. So if I click on this graph and move it and see from above, it kind of looks familiar. Like we see here, we see filaments. There are filaments. And then we see these higher peaks, and this corresponds to regions of the disk which are brighter. And this is exactly what we see here. So this graph corresponds to the reconstructed view, but except that instead of converting the values as pixel intensity, it is basically now a 3D view. And let's explore why it is particularly interesting to do that. So to show you the interest, we also have to discuss this graph there, which is basically the average profile that you have here. So this line tells us that what we are observing here is in the middle of this H-alpha line. So we're at the lowest intensity of the H-alpha line, so we're in the middle, the center of this line. So that's the H-alpha line that we're observing here. And I can go again, show you that. That's why this image looks very much like the reconstructed image at pixel shift 0, because this is exactly what we're seeing there. So now what's interesting is that I can click here and it would show me something off band, slightly off band. So we're moving towards the continuum. And as we move to the continuum, we see that it gets flatter, but with more intensity. So maybe at this stage, something that you want to do is to change the scale to go to a square scaled, so that you actually can see the variations in intensity even at something which is as tiny as the continuum, because we're basically squaring all the intensities. So the highest values are going to show better than the lower ones. So if we go actually to something which is flat, like the deepest in the H-alpha line, using square is not super interesting, but you could want to use a logarithmic scale instead. So this one is log 2, and we could have log 10, which even makes it even more interesting, especially if you go near the edge like this. This is basically a prominence that we are seeing there. Like this intensity is at the edge of the disk, like the limb, and it shows very much in logarithmic scale, but if I switch back to the default scale, which is linear, you see that the intensity is much lower. So in case of H-alpha, you can see that quite easily, like these prominences, but sometimes like if you go to the helium line, it's not as obvious. So switching to a logarithmic scale and looking at a particular wavelength is interesting. Okay, so we have that, and something that you can do is that you can actually So we're selecting the middle there, but you probably want something like seeing the evolution based on the wavelength. So you can click on play, and that's exactly what it's going to do. Like now it shows you the intensity based on the wavelengths that we're observing. And then you can stop at some point and say, okay, this one is interesting, let's explore what we have there, export to PNG, or you can choose to export a video, in which case it's going to play this whole wavelength range and export a video which basically contains all of that. I'm not going to do that now because yeah, it would be not super interesting for the demo, but you get the idea, just explore. So, so far what we've done is that we've explored 2 dimensions, X and Y, and then the intensity is the pixel value. But now what we can do is actually change and choose a different slice. And for example, I'm going to select the slit position slice. And now you can see that what we get is quite similar to the other graph that we had there, which was the 3D spectral profile, except that there we're not looking at average data. We're looking at real data on a particular position, and so that's a particular frame in the file. So particular slit position, sorry, because I chose the slice slit. So at the particular slice slit position. So if I click on the disk now, what I'm moving is the position in the graph regarding one dimension, which is the frame, but the other dimension this time is the wavelength. So we're observing the differences in intensity based on the wavelength on a particular slice. So again, I can play that, and you will see that it looks very much like the reconstruction, like what you see when you're actually doing a scan. Like it widens and then suddenly it becomes shorter, and that's exactly because we're scanning this disk in one direction. So I can stop and I can choose the other direction, which is this time the slit, and now we're moving in the other vertical dimension, which is the slit. So we take a frame and then we are basically moving the slit position. So this is exactly the same, except that you're looking at another direction. So this graph is super nice because depending on when you're going to position, yeah, this one, for example, you see that we have bumps there, and that's basically the intensity that allows us to reconstruct the image of the sun in the middle of this H alpha line. And when you're looking at the valleys like that, basically what we're seeing is the Doppler effect. So the movements that we have there, like the bumps and whatnot, are due to the Doppler effect. So it's super nice to observe and see that in 3D. So again, I can play this animation and then you kind of see what's going on during a scan, except that you can see that in 3D, which is, I think, super nice. Okay, so that's for this spectral cube, if you will. And now we're going to go to the last improvement in this version, which is called the spherical tomography. And I'm going to click on that, and again it asks some questions, and it's actually fairly simple to answer. You should keep the default in most cases, at least for H alpha. So we want to explore the graph like this profile. We're going to explore it either towards the blue, so to the left, or towards the red, so to the right. And the reason we want to do that is that basically there's a physical effect, which is that depending on where we are, so whether we are in the center of the wavelength or on the wings, we're observing at different altitudes in the chromosphere. So it would be nice if we had a way to visualize that in 3D, and that's exactly what this is about. So I'm going to click on generate. It takes a few seconds to create something, and then boom, you see that. And that's exactly looking like the initial 3D view that I showed you, except that it is a bit blurry on the edges, and we're going to understand why in a few seconds. So it moves, and then I can stop there and select it and move it. And if I move it to the left slowly, I'm moving here. You see that the prominences are actually showing up through the chromosphere. So we see that they're actually higher than this base thing, which is lower in altitude. And the lowest point is actually at 1.5 angstroms, and the highest, the middle of the H alpha line is actually at 0 angstroms, and that's the highest in the chromosphere. So this maps everything into a 3D dimension. And that's why you have this slider there, because what we're seeing doesn't have real physical dimensions. Like, it is exaggerated, otherwise we wouldn't see anything, because basically the altitudes that we're talking about are much smaller than the actual scale of the sun itself. So if I go and go to the minimal, the image becomes flat. But if you really want to see something within, you can basically zoom to the maximum, and you would see by transparency something which is happening. So the grayscale view is interesting, but I don't think that for this exercise it's the best thing to choose. And I'm going to actually go to the color map and tell you to select red to blue. And let's see what's going on there. So when we do that, we're actually seeing something which is more advanced, because the algorithm which I developed to do that is basically based on some physical reality, like the transparency of the chromosphere based on the intensities that we see in the actual images that are used. So in this case, we have 5 different images, and the red regions are basically much lower in the chromosphere, so it corresponds to the photosphere. And the blue ones are higher, like they correspond to these filaments. And you see, if I move again there, you see that we can see them by transparency. And the purple ones are basically in between, but it shows that there are some details coming up from the photosphere. And the green ones are mid-atmosphere, mid-chromosphere, I would say. And there is an issue on the near the limb, but it is very similar to the limb darkening that you have typically on images. So there is some correction applied, but not enough. But I want to keep some reality in this graph. So again, you can move and exaggerate the dimensions if you want to, and you could actually see the different layers there. Like this one, which is the deepest, is red. Then you have green, and then you have blue. And when we move there, we basically see what comes through. So it's much more interesting than this mono view, which is it is more correct in terms of what you would see, but it is not correct in terms of what is higher, what really comes from the inner layers of the sun, what comes from the outer layers. And to make that even more appealing to you, let's select this button. So I'm going to select this one, the first one, 0 angstrom, and come back to mono. And what you see is basically the highest layer in the chromosphere. So that's our typical H-alpha image. But I can select instead the deepest, which is the photosphere. And we see that now. So that's in the continuum, and we have the photosphere showing up there. But I can select other layers, so select only 2, and then you're starting to see some details. And as I add more, you see that the contrast is basically blurred, which is normal because we're mixing several layers into one, and that starts looking familiar if you're actually using some etalons which don't have quite some very narrow bandwidth. Like, you could see something which looks like that. And again, you can basically restrict that, and that's combined. So there is some image which is combined there. And I can go and select, let's move back to red-blue, and if I unselect and only keep the lowest and highest layer, it's basically showing you in green because there's this red layer which is thin, very thin there, and the other one, let's increase that. You have that, so the red layer, the green layer, and the blue layer. So depending on how you exaggerate, you can see these. So there's something happening here or here, like we see that the light is coming from the center. So very nice. If you want to, you can also enhance the contrast, and that's even more visible what comes from the lowest layers. And you can also show the prominences, even if maybe that doesn't make much sense here. So okay, so that's all I had for you. Again, of course, what's interesting is to maybe export that. So you can export either a PNG image, or you can create again a video. And if you create a video, it's going to do the what you get if you actually do this. So click on Spherical, generate. If I do nothing, you have this. If I select the red to blue, then you see this moving, and if I do export, you're going to see that video moving. So nice stuff for you, I guess. Thanks all for listening. I had really a lot of pleasure developing that. It took me quite a while to manage to do that. Again, unfortunately, it doesn't work for the Mac OS X users, but no hardware, so I wish that you could all use open source software, but this is not how it goes. So thank you everyone, and bye-bye.